how the electron shell structure relates to its location on the periodic table. So you've got a periodic table at the front of your booklet. Periodic table is made up of groups and periods, right? The group tells us how many electrons are in the outer shell, yeah? If we ignore the middle. And what annoys me about this diagram is there should be 10 elements there, not 7. So it's illustration, but not a correct one, right? And similarly, there should be more than 5 here. There should be 6. So if we look at, as we go across, we go group 1, group 2, 3 through 12, 13 through to 18 as we're going across. So ignoring that group 3 through to 12, right? Group 1 has how many electrons in the outer shell? 1. Group 2 has how many electrons in the outer shell? 2. Group 13 has how many electrons in the outer shell? 3, yeah? So take the 10 off from the 10 that we're skipping past. So group 14 would have how many? 4. Group 15 would have how many? 16? 17? 18. 8. Fantastic. So, and then the period, right, is the horizontal rows, and the period tells us how many electron shells there are. So period 1 has how many electron shells? 1. Period 2 has how many electron shells? 2. Period 3 has? Period 4 has? And so on, right? And we don't really need to go beyond element 36, okay? We only really go up to 30 in year 10 and 36 in year 11. Okay, so the electron arrangement, the number of shells as we're filling them up gives us the number of periods. So we've looked at all the way up to 20 after yesterday, 288, right, for argon. Then we go to period 4, and we talked about briefly, right, so I'll mention it again, when, remember that rule is we cannot have more than 8 in our outermost shell. So when we fill up our third shell, we start to fill the fourth shell, and then we backfill the third shell. Okay? I'll say that again. When we fill our third shell, we start to fill our fourth shell, and then we backfill our third shell. What I mean by that is we go potassium and calcium. We go 1 electron in the fourth shell for potassium, then 2 electrons for calcium, right? And then we start to backfill the third. Knowing that we can fill a maximum of 18 electrons in our third shell, okay? And we notice on that fourth row, I've got 18 elements across there. So what's happening is I fill 8 in my third shell, start to fill the fourth, and these 10 elements from 21 through to 30 is backfilling the rest of that third shell, right? So in year 10, we're only looking at whole shell numbers. So when we progress to year 11, IB or VCE, we look at what's called subshells. So there's a subshell that we can fit 10 electrons in, and that's why we have those 10 electrons in that middle group there. So we backfill that third shell. So scandium, we go to 9, titanium 10, vanadium 11. What do you notice when we get to chromium? Right, we skip 1, right? So instead of going 12, it goes 13, 1. So it's an exception to following that trend, right? And this also links in with subshells that we're not talking about in year 10. So it's more energetically stable to half fill those last 2 subshells, is why that occurs. Manganese, iron, cobalt, nickel continues with that trend. Then we get to copper and we buck the trend again. We fill that third shell and half fill that next orbital or subshell. So our 2 exceptions to following that trend are chromium, where we go 13, 1, and copper, we go 18, 1. Does that make sense? Yeah, question? Why? It relates to subshells, right? It's about the favorability energetically for where those electrons want to be placed. Yeah? Without going into too much detail about subshells, I don't want to confuse you yet. All right? If we think about it, that it's just an exception to the trend, and then we can explain it more next year for those who want to continue. And I'll give you some details, and I'll give you a video that goes through subshells for your interest. Okay? All right. Our first crack, which we're doing in the start of our double on Tuesday, is called flame tests. We're going to have a range of different chemical salts that we're going to put into a Bunsen burner. Right? We're putting it into a Bunsen burner and it changes the colour. Right? It will change the colour of the flame, and different metal salts result in a different colour. And the reason that that happens is in elements, right? In elements, electrons sit in their shells, and as we give those electrons energy through the flame, right, giving it a lot of energy, that electron becomes excited. Right? So what happens when you drink a Red Bull? You have excess energy, you become excited, right? You want to hit the dance floor. So this electron is excited, it's got this excess amount of energy, it's jumped into a higher shell, and it's dancing around. It wants to get rid of that energy, and so the difference between the energy levels of those two shells, it will emit as light, right? So what an electron shell really is a discrete energy level where electrons occupy. So if we think about it as more as a energy level than a particular region of space, right, then that helps us to understand that there are differences. Question?
What do you mean by discrete?
Discrete, right. So there's two definitions of discrete. What's one of them? Subtle. Hiding, right? Discreetly hiding my keys, my wallet, my phone, right? That's one definition. The other, think about maths. You've got discrete versus continuous variables. What are they? What's the difference? Have you looked at discrete versus continuous variables in maths? All right, what does the word continuous mean? You should know what that means. Ongoing, right. So shoe size is discrete, yeah? Only goes up by halves. So I don't have a shoe size that's 12.1375, do I? I can have 12 or I can have 12 and a half. I can't have in between. So shoe size is discrete. Measuring your height is continuous. Yeah? Question?
No.
So what I mean by discrete energy levels is it can only occupy certain levels. Yeah? Like floors in a building. I don't have a 2.5 floor. I've got level 2, I've got level 3. If I jump into an elevator, there's no 2.5 button in an elevator, right? So in order for me to get to level 3, I have to push the 3 button. I don't transition through space, ignoring stairs, right? Yeah, question? Subtle?
Yeah.
Subtle means small, a little bit, not much, right? Not obvious, yeah. Cool. All right. Hydrogen emission spectra. This is particularly for those who are doing the IB next year. So n equals 1 is the ground state for where that electron occupies, right? We've only got one electron in hydrogen, right? Make sense? We've only got one. And when I give it energy, if I give it enough energy, it jumps to shell number 2. If I give it more energy, it jumps to shell number 3. If I give it even more energy, it jumps to the next shell, and so on. As that electron transitions back, the bigger the jump down, the greater the amount of energy, right? And the different coloured light it will emit. So blue light or violet, and then into the ultraviolet, is high energy light, which is why ultraviolet light from the sun burns your skin. Violet light doesn't. So I can shine a blue light on your skin, nothing will happen. Ultraviolet light is enough energy to break the bonds within your skin and cause a burn, right? So red light is low energy. So the smaller the distance or difference between energy levels and electron jumps will be in the red. Greater the distance, we're moving from Roy G. Biv, right? Red, green, blue, indigo, violet. If any of these back to 1 will emit in the ultraviolet. And there it is. That finishes off for our first topic area.